Hello IB. I thought we'd do a quick video for 17C on optimization. My voice is a bit husky, having done the swimming carnival yesterday. Anyway, optimizing, we're trying to find obviously the optimal solution. The optimal solution is going to be a Y value. What gives us the maximum Y or a minimum Y? And that will occur at a particular time or condition. That's our X coordinate. So that's why I've got to remember that's our optimum value. The X coordinate is when it's happening. We're obviously looking for a maximum or minimum. That's a stationary point, or it could happen at the end of a domain. So always just check what is your domain and whether that is your optimum situation. To find your optimum value, you're either going to just go straight to your GDC. If you're in a calculator paper, graph your function, find your maximum or minimum, and you can get your rounded answer, or it might be exact. Otherwise, if you're not in a calculator paper, then you're going to differentiate it to do your differential calc to find your turning points, and that will give your exact solution. So we'll look at that in more detail in a moment, but that's one way of doing it. Otherwise, if you're in a quadratic, you can just simply find the vertex, your X value for the vertex. So remember, this is where our X is equal to that. It gives us when it occurs. It doesn't tell us what the maximum or minimum is. So don't forget those basic rules rather than having to go through all your calc. In your differential calc, remember that when you take your first derivative and solve it equal to 0, that's going to give you your stationary points. So set up your equation, if needed, with appropriate variables. Check to see if at A is a maximum, minimum, or horizontal point of inflection. So this is the important one because that's meant to be a star. When f dash x equals 0, then it's a stationary point, and you don't know whether it's a maximum, a minimum, or that horizontal point of inflection. So the only way you're going to tell that is from your sign diagram. So in this case, if it's a maximum, then the original function would have been going upwards, giving it a positive gradient. So this is a sign diagram for f dash of x. So initially positive gradient, then at A where you've got your stationary point, it would have been horizontal, 0 gradient, and then a negative gradient. So that means at A you had a maximum. Obviously, if it's a minimum, you would have gone negative, 0, positive, and a horizontal point of inflection. Remember, there's no change in the sign. It would have been positive, 0, positive, or negative, 0, negative. So check with back on section A, 17A, if you'd forgotten those things. Check your endpoints of the domain, if they're the maximum or minimum. The other way to do is to use your second derivative to check for concavity. So at the point, if the second derivative at that point is greater than 0, that means the second derivative is positive. That happens when we have concave up. If it's concave up, then in that case we have a minimum. If the second derivative was negative, then it would have been concave down and we had a maximum. And obviously using your GDC. So we'll run through two fairly typical examples here. Something like this first one, these are just from the textbook. This could come up in your IB papers. It's a fairly common question where you've got a piece of metal plate, you're cutting out the corners and folding it to make your volume. Here we're going, let's cut out X. They said you've cut out, what size must be cut out? So define your variable X. That means this side here is going to be 25 minus 2 lots of X for these X's here. And the other side, which was 40, you're taking away 2 X's. So your volume is going to be length times width times height, expand it all, and you come up with this cubic function. To set your domain, and most real world problems have some sort of restriction or domain, then think X has obviously got to be greater than 0 because it can't be negative and obviously doesn't want to be 0. And then we want 25 minus 2x, that's this section here. We want that positive. So when we solve this, we're getting 25 is greater than 2x. So therefore, x is less than 12.5. That went a bit funny. 12.5. So therefore, our x must be between 0 and 12.5. Let's assume we're not in a calculator paper. And so we take your first derivative, and that's differentiating this function here. We'll come out with this. Factorize it if you can. Then we're going to solve that equal to 0. When you solve that equal to 0, x is either equal to 5 or x comes out equal to 16 2/3. Given our domain is this, then that cuts out this option and makes this our only solution. So our x value needs to be less than 12.5, can't be 16 2/3. What we then can do is, with our first derivative function, we can test some points and come up with our sign diagram for our first derivative. So remember, we're doing, we don't want f, we're doing v dash x. So your sign diagrams for your derivative function. At 5, we've got a zero first derivative. That's where we've got a maximum or minimum or something happening there. And then we just want to go, well, what's happening less than 5? What's happening greater than 5? So if you think, if you put in 1 here, if a 1 goes in there, you're getting a negative number. That will be a negative number as well. Negative times negative makes positive. So when we're doing our first derivative, test our points, v dash at 1. That ends up being 4 times a positive number, a negative number, times another negative number makes a positive number. So that's how we get that positive. Test a point bigger than that, say 6, and we'll end up with a negative. So those positive and negatives are telling us about the derivative. So if we have a positive derivative, it means our original function. So this green one here is what our original function is looking like, our cubic. So that's saying at this point we've got a positive gradient, a 0 gradient, a negative gradient. So that tells us then that we've got a maximum. At that point, we could stop. Otherwise, if you weren't sure about that or you wanted to go one step further, we can do our second derivative test by taking our second derivative, differentiate this function back up here, and we come down with, let's go purple. So we're going to differentiate that down here, and we end up with our 24x minus 260. Substitute 5 to see what is the second derivative at our stationary point. Substitute in, we get minus 140. It's negative. If we have a negative second derivative, that tells us we are concave down. All right. So all those rules that we learned in 17A come into play here. So concave down, which means we've got a local maximum. If we test our endpoints at x equal to 0, then we don't have a function. Or don't have our box, because that would be 0. We've just got a flat piece of metal. And if x is equal to 12.5, again, this side would be 0, and we don't have a box. So this is our local and maximum, global maximum. The other example is this one where you've got a set amount of fencing. Have a quick read of it. Pause the video if you need to. We've got 300 meters of fencing. We've got 2 sides, and we want to say, well, what's the maximum area we can get with our 2 sides? To maximize the area of a triangle, we're going half base times height. So this is our base, there's our height. And to get expression for the height, we need to use Pythagoras. So in this example, they step you through that. And in the IB, they would do the same thing. They'd step you through your first part, show that, so that even if you couldn't show that, you could keep going in the second part. But obviously, this squared is equal to that squared plus that squared. Solve it, rearrange, and I'll let you just crunch through the algebra there to make sure you're happy with that, to come out with our length AC. So our area of the triangle is going to be half base times height. So it's a half AC times X. That gives us that expression here. Now, this one, to then go through and find our first derivative and equate it to 0, you would use this equation. And if you're on a non-calculated paper, remember this is a product rule because we've got this function times that. So use your product rule. And then once you've differentiated, equate it to 0 to find your stationary points. This method here that they've got in the textbook, it's a little different. What they've done is, instead of doing this with the square root, they've squared the function and basically said, if you square the function, it means all the function then becomes positive, and any maxima will get sort of, will stay as a maximum or a minimum, or won't be a minimum, yeah, depending where the function is. And so when you differentiate it, you'll get the same point, but that you need to think through, and you may not have thought of doing that in an exam. You would think of differentiate it, get a dash x, and equate it to 0. That'd be some solid algebra. If you chose to graph it, then what you'd do is you'd be putting that in your function, in your calculator, and it looks like this when you just put it in. And that's because our window, when we look at what we've got, our window settings, usually it's like it comes up with those sort of numbers. If we, in those situations, what you could do is either go to your window and do a zoom fit, and that comes up, which is still not a lot of help. Otherwise, what you could do is go to your table, Control T, and look at some of the values and go, well, we're at hundreds here, keep going down. All right, we're going down, we're getting 1,000. At 12, we're getting 1,000, 1,800, 2,000. Keep going, and you're just scrolling down. We're getting really, really big numbers, all right, up to 5,000. At some point, you might just go, well, let me guess a number, or how long do I keep going, because it's still not decreasing. I've spent some time already looking at this and found out that if I set my menu, my window settings, -10 will leave that one. I know to put this at 2. Oops, go back. Where are we? Go back up there. If I make this at 200 and I do a minimum just so I can see the bottom axis, I like seeing the bottom axis. And if I put this at 10,000, then I get that nice looking function. And so I'm going to shift that out of the road. From there, I can then just analyze the graph and get the maximum. We find the maximum here. Let's have a quick look at analyzing it. Maximum, lower bound here. Maximum occurs at 100. So at 100 is where our maximum occurs, which is what they've come out with down here. So our maximum's at 100. It's saying what is the actual area that is the maximum. You then substitute it back in the original function to get your area, or get it from your calculator at 8.66 times 1,000 gives us 8,660. Hope I'm not going too fast. Anyway, there are 2 examples that we've gone to, and the optimum situation is a maximum. One of the questions in your textbook, and we'll have a look at this in class, this one here is about productions and how much does it cost. In this case, it would be nice to minimize our cost for the production. So here we're after a minimum on our function, not a maximum. So it can be either those two situations. To get the optimal solution is a minimum y value or a maximum y value. So have a look through that. Make sure you're confident with how to use your first and second derivative, and then we'll look at these examples in class. Thanks for listening and looking forward to seeing you. Bye for now.